tampoco mucho al detalle, sino presentar generalidades. Ya se han realizado dos muy buenas conferencias que seguramente, y esta de Siri tendrá una muy buena acogida también, que es un tema general y que será gran parte del futuro de nuestro trabajo en sistemas eléctricos, que es la analítica de datos y en empresas eléctricas. Antes de empezar, quiero compartir un poco para que conozcan qué son los comités técnicos de IEEE, de IEEE PES, mejor dicho. Son grupos de trabajo que se encargan de estar atentos a grupos de interés asociados a normativas y documentos. Estas temáticas en el sistema eléctrico son muy diversas, que tratan de analítica en sistemas de potencia, maquinaria eléctrica, energía y desarrollo de generación, energía e internet, almacenamiento de energía, aislamiento, redes inteligentes, sistemas marinos, energía nuclear, mucha variedad en sistemas de potencia como comunicaciones, dinámica, instrumentación, operación, planeación y economía. em, el, de protecciones y control, también de renovables, smart buildings, subestaciones, eh, protecciones y descargas, de switchgears, transformadores y de distribución. ¿Qué se requiere para pertenecer a estos grupos? Simplemente ser parte de IEEE si tienes el interés, preferiblemente al menos un background básico para, para estar pues atento a los temas. No es necesario ser un experto, pero sí tener algún background para trabajar. Por ejemplo, yo hago parte del comité de maquinaria eléctrica por mis funciones profesionales relacionadas con especificación de generadores. Estoy trabajando en este momento en el comité de el estándar IEEE C5012 de generadores y motores. Eh, Relacionado al tema de hoy, seguramente Siri Varadan debe ser parte de este comité y debe trabajar con este tema de redes inteligentes y tecnologías emergentes que, que trabajan estos temas asociados a la presentación. Muy probablemente él haga parte de estos comités, y seguramente lo es, porque para ser un conferencista distinguido de IEEE, pues normalmente la gente hace parte de estos grupos. Okay, before Siri Varadan presentation, I want to introduce him. He's our presenter today. His lecture is called "Using the Power of Data Analytics in Electric Utilities." Is the Global Director of Asset Management from ABB Hitachi, or I don't know how to pronounce it.
Yes, Hitachi ABB.
ABB. Okay, thank you so much. He's a PhD. As I said, a Global Director of Product Management of software products related with asset management. He also had worked with Wilsol, Aston, Kima, Nexan, and ABB. He's the author of Shaping of an Energy Engineering Career Advanced to Management. And he also contributed author of Smart Grid Advanced Technologies and Solutions. He's also, I haven't detailed it, is a DLP from PES. It's not a easy to be in this part. They have a lot of requirements to be a DLP from PES. The PES, excuse me. There's a requirement. The first one and the most valuable for me is the will for share the information with the people. And thank you so much again, Siri, for being for us. And that's all. I I will stop sharing my screen now for your presentation. Thank you so much.
Okay, thank you very much. I want to thank you very much for the kind introduction, and it is a pleasure and my honor to be talking to you, to you all. Give me just a minute. Let me start sharing my screen. Okay, can you see my screen?
Yes.
Okay, perfect. Okay,
Okay.
so we'll go ahead and get started then, Sebastian.
Yes, we
Okay,
start. It's
now
good.
just before I start, tell me what is the time expectation? How long do we need to, how long do we have?
Normally it's a hour and a half
Okay.
of the presentation and 20, 15 minutes for questions.
Okay, all right. Okay, perfect. Okay, let's get started here. I'll put this also in the slide. There. Okay, right? Okay, thank you very much for the kind introduction, Sebastian. I'm honored and it's a pleasure to be talking to you and sharing with you what little bit I know, right? I have been working in this field of electric utilities for the last 31 years, and I have been um, working predominantly from a consultant and from a vendor perspective, um, in creating a lot of new products and creating a lot of new ideas that are then implemented in the utility side of the business. So I have a lot of experience working in control centers, working in transmission and distribution control centers, working with different systems, and also working with the assets that the electric utilities use in order to be able to provide power to the end users. Okay. One thing that is happening in the last several years is the role of data, the role of making sure that you do something with that data in order to, uh, you know, take that and use it for different purposes. That is becoming more and more and more important in the work that we do today. Okay, so my presentation will mainly focus on um, essentially the power of data analytics in electric utilities. I will focus on asset management since that is my area of specialization. I specialize in asset management, which includes asset monitoring, performance measurement, and aspects related to the asset investment planning. Right. So those are my areas of focus and specialization. So we'll talk about how this, data is, a key driver for all the stuff that we do. Okay, so I'll go on to the next slide. So the goal of my presentation is to give you a high-level understanding of the role of numbers and data in an electric utility and focus on transmission and distribution asset management use cases, right? We will go through multiple use cases. I will show you some examples. We can even go through some mathematical examples, and you can see how the logic in a typical software program would work from the perspective of solving a problem related to asset management. Okay. I'll start first with just talking about data. Okay, data in a very general context, and talk about some of the different ways in which you can do things with that data. Okay, then we'll get into the world of electric utilities and try to understand where is the data being created. You know, what types of data are created. What can you do with that data, right? And then we get to the next part of it, which is what do you do with that data, right? So you need to understand the data in a particular context. You need to understand, how, we can then deal with asset management from an electric utility perspective. And then we look at use cases in asset performance management and asset investment planning. Those are the two uh, abbreviations here: asset performance management and asset investment planning. Then we'll do a deep dive into a transformer, right? Transformer is one of the most important, most critical, most expensive assets in a substation. So let's do a deep dive into a transformer. Many of us look at the transformer and all we see is a big, you know, piece of machinery. And we would never think that there are numbers coming from this. But in this presentation, we look at all the numbers that come from a transformer and what do you do with those numbers. I'll then dig into a little bit of the state of the art, in what is current technology in today's electric utilities. And this is based on my last 12 years or so of working in the asset management field, developing products and implementing these products at various electric utilities in all over the world. Okay, so let me go to the next slide. Any questions so far? Are you clear with the outline and how I want to walk you through this journey? Okay, any questions? If you have any questions, please interrupt me. In Teams, there is a way you can raise your hand. Or Sebastian, if you want to, quickly interrupt me when you see the flag go up, just let me know and
Okay,
we can
okay.
stop and answer, because I have two screens here. On one screen is the presentation that you are seeing. On the other screen, I basically have the sneak preview of the PowerPoint. So I don't see the other, the Teams.
Okay, okay, we'll tell you
So
when.
if you see a hand go up, just stop me, okay? All right, very good. So let me go here and talk about data. So when we think about the word data, we're thinking numbers. We're thinking about zeros, ones, and we're trying to see, how all those zeros and ones, what makes sense. Data is basically raw observations that could be, without any numbers. They could just be raw observations. Data can come from sensors, they can come from measurements, they can come from human social interactions, they can come from financial transactions, they can come from any number of sources, right? They come with different velocities, they come with different volumes, and they come with different varieties, okay? So the key question is, what do you do with all of this data, right? Trivial fact here is, in 2020, this was the estimate of how much data one person would create in every second. Okay. Now here we're talking about, the digital age, where people are texting, and ultimately texts and messages and WhatsApp and Signal and Telegram and all of these things become, zeros and ones, and they get stored somewhere in the internet. So that's what we're talking about. And on the right side, I basically have something that is, more related to a safety message, which I'm going to talk about. Now, this has really not much to do with data and electric utilities, but you will see the connection very slowly. Okay. So what I have on the right here is also data. Okay. This is data related to COVID, coronavirus risk activities. And as you can see here, this is just a spreadsheet. And when you look at the spreadsheet, you're thinking, yeah, this doesn't make any sense here at all, right? It's so boring to look at data, especially when it is in this format. But look at this next slide. The same data that was there in the spreadsheets has now been put in a very beautiful way, where we've taken that data and converted it into a beautiful safety moment using the power of visualization, using the power of different objects, right? So in this case, we're using round objects. We're using, a timeline here or a scale here that talks about increasing risk. And we're talking about different colors. If you see here, this is yellow, and as you go from here to here, it's becoming more red. And I can make this even bigger by using different sizes if I want to show the impact, right? So the key thing that I want to show you here is data that look like this, okay, which is dull and boring, and nobody would look at it more than once. Anybody who's adventurous would look at it and be like, okay, I see some things in here, but I really don't understand it. But when I put it in this format, now suddenly it becomes very useful. It becomes something that you can, understand. It becomes something that you can quantify. It becomes something that you can tell a story with. And the whole idea of data analytics is to be able to tell the story. Okay. Now the numbers basically will tell you a partial story. Then there are anecdotes that complement this, and that is how you get the whole story. Okay. Now, one additional thing that I also want to point out here is in just looking at this picture here, the amount of information that you get is immediate. So anybody who looks at this says, oh, going to a nightclub is very high risk, so I need to avoid that. But on the other hand, if I'm going to go play tennis, it's okay, not so bad. So you see right away, I don't need to look at, what is written exactly in each of these, circles here. But just by the color, I can say, okay, these activities here are good, these activities here are not good for me, especially if I want to, prevent myself from catching COVID. Okay. So the key thing also to understand is that in all of this, the data visualization makes a huge, huge impact. And combining the text, combining non-numeric data with numeric data gives an entire new twist to how you can visualize data. The other way, of course, and you probably seen enough of this, over the months here, is if I look at something like this, and let me pull the screen here to show you what I'm talking about. If I show you a chart like this, right, and this is from the World Health Organization, this becomes even more interactive, right? So these are what we call dashboards. These are what we call different ways to visualize the data, right? So right here, I can look at, different ways to filter this data. I can look at, each of these different countries. I can see what are the numbers associated with it. So my idea here is not only do I want to give you a safety message, but I also want to give you a very key thing, key point is that data is not static. Data is dynamic. Okay. Data changes. You can watch that change in data over a period of time. You can characterize the data with different colors, sizes, and shapes. And all of this is very important in telling the whole story. Okay. So you have to understand that at the end of the day, you must answer the question, why do you do something, right? Because if you can answer the question why, then doing, the what is very easy. So that is what you need to understand about the power of data. Okay, let me go on to the next slide. Now, how is this useful from an electric utility perspective? So we know, and here if I take a typical vertically integrated utility, there is generation. The generation is typically stepped up so that it can go through transmission at a high voltage, and then it's basically distributed, stepped down, and then through distribution lines, it basically is provided to the end user. There are transformers typically on the pole tops here that basically bring the voltage down to, the needed level, which is either 110 or 220 volts that is consumed at the residential level. Now here, there are multiple assets in this energy delivery chain. So for example, if I look at a generating station, I have generators, I have turbines, I have rotating equipment that are creating data, right? Rotating equipment that are producing, that are spinning at a certain rate, that are basically creating, data. If I go into, the transmission system, again, there's a lot of data that is coming from here. And now the megawatt flow, megawatt flow, we are looking at the um, different flows in different lines in the transmission network. Then when I come back here to this level again, I have, distribution flows, I have reliability, related things that I can calculate for all of these. And then I have the transformer, and then finally the meter. And the meter is also generating data, because for all the energy that is used, there is a record of it. And so it's again another piece of data. So as you can see here, we have different types of data, right? Different speeds of data. When I say different speeds, that means that the data is created at different speeds, right? So for example, if I'm looking at a rotating equipment here, and I'm looking at the speed of the shaft, right? And let's say my sampling frequency there is very high, then the data that is being generated and sensed and stored is at a very high frequency, right? And it is, in this case, I'm measuring, say, the RPMs of the generator. Now, I could also be measuring other kinds of things, right? For example, how much is the fuel consumption of that particular turbine? Now, for that fuel consumption, I can look at it at a different time scale. I can look at it as how much fuel is consumed in a day, how much fuel is consumed in an hour, right? So different time intervals. Um, at the end of the day, again, remember what we said is, what is the total story? What is the complete story that all of these different pieces of data are telling us, right? And the answer is it depends. It depends on the story you want to tell, okay? So I'll show you exactly what I mean. You look at this picture. I'm not sure if there's a translation of this in Spanish, but this is a book that is a very famous book that uh, many of the children read growing up, reading English. Um, and this is the story of Alice, who is going through Wonderland, and she meets different sorts of characters in here, and then there's an interaction that goes on between Alice and the different characters she meets. In one of the chapters, in chapter 6, I believe, she runs into this guy, this Cheshire cat, and Alice asks the cat, "Would you tell me which way I ought to go from here?" And the cat says, "That depends a good deal on where you want to go." She says, "I don't much care." Then the cat says, "Well, it doesn't matter which way you go. If you don't care, you can go any way you want and you will get there. So long as I get somewhere," Alice says an expression. She says, "Oh, you're sure to do that," said the cat. "Only if you walk long enough." So the moral of the story here is this: you have data from every place. You have data coming in all of these different segments. Question is, what do you want to do with that data, right? If you follow that data, logically to the next step, and ask the right questions, then you will get you will get the answers that you're looking for. So I use this as an example just because it makes a lot of sense. People can identify with this objective. Okay. So let me ask some questions. And in this case, I say asking the right questions to build the use case. Okay. Use case is a typical way in which we look at, we define it from the user's perspective, and we say, as a user, I want to see how much power each generator is producing as a function of time. Okay, so that's a good use case. So if I pick a generator here, then I want to understand how much power is being produced over a period of time. Okay, and I want to visualize that, right? So clearly then from a visualization perspective, you can imagine y-axis, x-axis, and you can see the generation, the power generated over a period of time. Okay, good. We can do additional things with that, but let's get to that in a little bit. Or as a user, I want to see how much power flows into and out of a given substation at a given instant of time. So at 2 o'clock in the morning, I want to see what is the power that is going in and out of this substation, right? At 3 o'clock, I want to see what the same, power flow looks like. What does this help me do? It helps me create a load profile. Okay, I can do multiple things with that load profile at a later time, but at least I know in this case that as a user, I'm trying to define what I want to do with the data that is being generated in each one of these locations, right? Or, as a user, if I'm now going to look at the distribution side, and if I'm a customer here, I want to see how many outages have been experienced by a given customer over the past 30 days. And this is typical from the distribution perspective, where you want to measure things like, SAIDI, SAIFI, and all that. In this case, we are looking at a given customer. So there is a metric in that is used. It's called customers experiencing multiple interruptions. So you want to see how many interruptions a given customer experienced over a period of time. So these are the use cases that are defined by asking the right questions, right? So if you ask the right questions, right, that leads you down a path where you can then provide, for the answers. I take you to the next slide, and all of you identify with this gentleman here, and basically said, if you had 1 hour to solve a problem and my life depended on it, I would use the first 55 minutes determining the proper questions to ask. Because it's in asking those correct questions that you get to the answers that you're seeking. Asking the questions is actually the more difficult than finding the answers. Okay, and that is my experience with asset management. If you know the right questions to ask, trying to get the answers is relatively simple. And I'll walk you through some examples now, and you'll see for yourself. Okay? So we are now going to get into the field of asset management. Okay. What is asset management? Okay. Now, people have different concepts of asset management. If you ask a financial, somebody from the financial side, they will say it is the management of dollars, it is the management of, money, it is the management of the life cycle of the money, so that over a period of time, you increase the amount of money that you have, which, is a good definition from the perspective of, finance. From the perspective of the electric utility, what does that mean, right? So asset management is the holistic practice. Now, this word is very important. When I say holistic, that means you have to take into account many different factors. It is the holistic practice of optimizing investments in alignment with the principle of the line of sight. So what does the line of sight mean? Okay. Line of sight basically means this: you spend your money, right, or you make investments where you can get the most return from your investment. Okay. That basically means that you spend your money on assets or activities that minimizes the risk of system failure. It also means that you spend on assets or activities that maximizes the performance of the system. So if we are talking about an electrical system, Spending money on activities that maximizes the performance of the system basically means we want to increase the reliability. We want to increase the availability of a given asset. We want to make sure that and if you look at it from the other perspective, that minimizes the risk of failure. So this basically means that you want to take activities, maintenance, for example, or proactive replacements, or other operational type of activities, so that you don't have a risk of system failure. You have less number of outages. You have less number of or lesser duration of outages, even if you have the outages, right? So that is what this line of sight is. Look into the numbers, look into the data that you have, and then basically identify, where you need to spend your invest, or where you need to spend your efforts, or where you need to invest your dollars, so that you are achieving these objectives. Now, this is a simple definition. There is a complete treatise that has been developed by the ISO, which is the International Standards Organization, and that's called ISO 55000. ISO 55000 is a very important piece of work in the world of asset management, and that basically provides you guidance with respect to these different activities that allow you to follow the line of sight principle. According to that, if you look at the assets, and when I look at assets, I'm looking at transformers, I'm looking at circuit breakers, I'm looking at station batteries, I'm looking at transmission lines, I'm looking at capacitor banks. These are all the assets from an electrical perspective. Why are they assets? One, they are physical assets, they are not financial assets. Okay, so you have to remember that we are not talking about financial assets, we are talking about physical assets. What is the difference between the physical asset and a financial asset? In the case of a physical asset, the condition of the asset deteriorates with time. Okay? That is something that is very natural to anything that is physical. The condition deteriorates with time if you don't do anything. The other part of it is the condition can be improved with certain remedial actions. That is what defines a physical asset. And a physical asset at the end of the day has a finite lifetime, which means it will, ultimately fail. And the idea here is how long can you make it continue to provide efficient service? That is the goal of asset management. How long can you reliably have service from a particular asset, in over the lifetime? What actions do you need to take, right? So if we now get into the definitions of asset management itself, the key questions you need to ask then from a asset manager's perspective: what are my assets, right? And in our case, it's we know from an electrical utility perspective, we are talking about transformers, circuit breakers, station batteries, transmission lines, distribution poles, transmission poles. These are all the assets that basically allow the flow of power, the distribution of power from the generation all the way to the end user. The only way the electric utility satisfies its objective of safely and reliably providing power to the end customer is by managing these assets. If these assets fail, then clearly the objective here is to safely and reliably provide power to the customer. The objectives are not met, right? So that is the key thing you have to understand. What are the objectives, that assist, or what are the assets that basically assist in the objectives that I have? Now, clearly in an electric utility, It is a large system that covers, several hundreds of square kilometers, or maybe even several thousand of square kilometers. So it is very difficult to know where are my assets. So that becomes again a very important question, because assets are geographically distributed. And then the question is, if I have to understand what is the risk of failure associated with each of these assets, I need to know what is the condition of these assets, right? Is the asset in good condition? Is it in fair condition? Is it in poor condition? Is it ready to fail? These are the things I need to know. Why? Because if I know that, then I can decide what remedial actions I need to take to improve the condition, right? And in this case, if I'm looking at a large electric system, we have thousands and thousands of assets. The question becomes, if I get the condition and if I get the associated risk of failure for each of these assets, what do I do with them? Now suddenly there's a list of 10,000 things that I can do or that I need to do. Then the question becomes, for all of these actions, it takes effort, it takes money, it takes manpower, it takes resources. And I have a small budget. In an ideal world, if I had all the money, I would do all the work that I can. But we are talking about a world in which we have resource constraints, budget constraints. So the question is, if I have budget constraints now, what remedial actions do I take so that my objectives are still met? And what are my objectives? My objective is to safely and reliably provide power to my customers, right? So that goal is the desired objective. Now, you can add additional objectives to this. So we said safely and reliably. Now, if you are also a private enterprise, you can say in such a way that I maximize my profit. If you're an environmentally conscious utility, which most utilities are, you say, I want to do it in such a way that I minimize the impact on the environment. Now, with further things, you can say, okay, I want to do it in such a way that I am, sustainable. You can then say in such a way that I'm, ensuring that my regulators are happy with what I'm doing, right? So you can increase all of these objectives as you go. But the bottom line is, no matter what objectives you have, these are the questions that you will ask. These are the questions that you must ask. And these are the questions that you must answer in order to be able to perform asset management successfully. Okay. Okay. Now, what is asset management for an electric utility, right? So there are multiple things that go on in an electric utility. It's actually quite a complicated enterprise. And I will show you in just another minute how complicated it really is. But at this point, the way that we kind of split asset management from the perspective of the various activities that are needed to sustain an enterprise are as follows. We break it down into these pieces. We say there's enterprise asset management, there is asset performance management, there's asset investment planning, and then there's work management. Okay. So what are each one of these? What do these things do? So enterprise asset management essentially deals with the procurement of assets. It deals with all of the auditing, it deals with all of the accounting related aspects of the asset. So for example, how much money is spent on a particular asset to be acquired? How much money is spent on an asset for maintenance? How much money is spent on the asset through its lifetime? there is a lot of financial, related activities going on here, in terms of reporting, in terms of, all of these things here, right? Now, what is asset performance management? Asset performance management essentially is once the asset is commissioned in the field, then what are the different kinds of things that you need to do in order to monitor its performance? Monitor it in such a way that you are maintaining the reliability levels or monitoring the performance such that the performance is operating at satisfactory levels. Taking the right actions. Now, taking those right actions and implementing those right actions happens with a work management system, right? So in asset performance management, we identify the work and we prioritize the work in asset investment planning. And then whatever work is being identified and prioritized is then sent to a work management system for that work to be executed. Okay? So that is the reason why we break this field up into these following components here. It aligns up with the questions that we asked before. Sorry. It aligns up with these questions that we asked before, right? So that's the reason that we have that. If you look at this from a strategic perspective, asset management, there are multiple pieces here, and these essentially are a circle because the asset has a finite life, and you need to keep going back and visiting what your condition of the assets are, because you will have a replacement cycle that needs to happen. You need to plan for that replacement, and you need to order for the parts. You need to then have delivery, commission it, operate it, and monitor it throughout its life, and then understand what work needs to be done with that. And then at the end of it, basically allow for a replacement, and they call that asset salvaging and replacement. Right? So asset management in an electric utility. Take a look at this picture here. Okay. What I have attempted to do here is basically capture some of the complex interactions that are happening in an electric utility. Okay, I understand that this can be a little bit difficult to understand. So let me start off with this piece here. Okay. So let us assume that we are going to start an electric utility from scratch. That means there is no electric utility there. We are going to build it from the ground up. Okay, so what do we need to understand? We need to understand where are the generation resources. We need to understand where are the load centers, right? And then we basically need to understand that, in order to bring the generation, the generated power to the load, we need to have a transmission line, okay? And then the appropriate distribution network in order to get the power to each of these customers. Okay, now let's assume that that is built. So that original part was part of the asset investment. Okay, so we made this investment and we put this infrastructure in place. Then we need to understand how to maintain those assets, right? Maintaining those assets is again part of the overall operations and maintenance strategy that people talk about. In order to do that, we need to understand, okay, workflows. Okay, so for example, let's say we want to add a new transmission, add a new extension to your distribution feeder. So that work needs to be identified, that work needs to get initiated, and then you go through all of the project management cycle in order to build that line. Okay. Once that is done, then it is basically now commissioned, and once it is commissioned, it is now included as part of a real-time system, because now it is going to be monitored. It is also going to be included as part of your GIS, which is now the spatial system, so that you're able to see that particular asset on a map. The real-time systems basically are then able to, control the flows, and they're able to, look at the network flows in different parts of the network, and they can control the flows, using generation dispatch. Okay. Then, as a part of this, we have, let's say, some work needs to be done. The work is identified. That work needs to be sent to the people in the field, right? And the people in the field can do the work. And when they are done with the work, they need to report back to work management to say that the work is done. Let's say the guys in the field need to get some additional parts in order to do the work that they need to. They need to coordinate with work management so that the materials may then be procured and then be distributed appropriately and made available to the people who are going to go out to the field, right? So you see, there is a lot of complications. And then to support all of this, you need people with the right skill sets, in accounting, planning, HR, right? So if you look at this thing here and you look at all of the flows in here, this is quite amazing because each and every flow here is generating data. Each and every flow here has data that is either structured data or unstructured data. The data is generated here or being created here is coming in at different frequencies. It is coming in at different speeds. It is of different varieties, right? In some cases you have work orders, in some cases you have sensors, in some cases you have, dollar amounts. All of this is data. All of this is being managed, created in an electric utility. All of this needs to be managed. All of this needs to be understood, just exactly like the way that we understood how, with dashboards to understand, where, things are happening. You want to understand the health of the network. You want to understand the health of, the assets in the field. So all of these pieces need to be understood, and all of these pieces are easily understood using the same data analytics techniques that we have, that we looked at in the earlier case. Okay. So the idea here, let me just summarize so far. We have looked at some techniques for looking at data, visualizing that data, and now we are understanding where the data is getting created in an electric utility network. Because of all the complex interactions that happen between all of the departments, in an electric utility, data is being created, and that data needs to be tracked. That data needs to be understood. Why? Because you want to optimize, the use of your assets. You want to optimize your objectives, and your objectives in this case to provide power safely and reliably to your customers. So that said, let me take you through the next thing here. What this basically means is the data that is being created here, or the data that you see here, is in multiple forms. There's structured data versus unstructured data, right? Some of the key examples of that is, structured data means that, data produced in one can be related to, somewhere else. Unstructured data is you cannot, you don't have any such relationships, but it is very useful data nonetheless. And numeric versus non-numeric data, right? So just like we saw in the example of the COVID, right? We had numbers and we also had a lot of things that were non-numeric. So we see the same sort of thing in electric utilities also. And I think this third part here is also very, very interesting, because in a lot of utilities, you still have a lot of data in paper format. Especially when people go to the field and they take down, readings, inspections. They're typically writing down things on, a piece of paper. They bring that paper back, and, the supervising engineer or officer does something, with the next steps. But electronic versus hard copy, this is again a very key key distinction to understand, because we, in our work that we do, we have a lot of situations where customers have hard copy, information. So we actually convert that into electronic format so that we can use it for the other work that we do. Okay? Then the other thing that you also have to watch out is for formats. Okay, formats of data are sometimes very interesting because they can cause a lot of problems, and we see this all the time. Numbers versus characters, right? So for example, where you should see a 0, you see an O, and when you see it, they both look the same. It's very difficult to tell, or maybe the user, puts a 0, and then when it is translated into electronic format, they type O. But from a computer's perspective, 0 and O are different, right? So then there's the thing of text versus logical, cases where you have yes, no, fair, good, bad, and then logical, 0, 1. So again, these are different formats that you need to watch out for. Ultimately, we also have now more and more, and I will show you some examples of visual data and audio data, right? Visual data and audio data are, again, important, but what do you do with this data, right? How do you actually make sense of this data? And then there are other specific things, for example, regional differences. I know from my experience in dealing with examples from South America and Europe, the comma and the period are different. So for example, if I say 100.00, right, in USA it is 100.00, but in other places that actually means 100 followed by another 2 zeros, right? So in this case it is actually 10,000. So the comma and period. So these are some of the typical things that we come across in all of our data related activities. Now, again, this applies to all of the data that is being created here as a result of these multiple processes that are happening with different frequencies, with their own cast of characters, with their own tools, with their own databases. So each one of these has a different database. And if we want to look at asset management as a whole, we need to look into each one of these databases in order to make sense. Okay. All right. Let me continue on. Any questions so far? Sebastian, we're good?
Yes, we have no hands up, but I have one. But I think that you will talk later that how to uh, get on with these kind of problems and these formats and regional differences.
Yes, yes. So we'll talk about that. Once we understand the difficulty, once we understand the intricacies of the problem, let's then talk about the solutions. Okay? So, okay, good. Okay, next question is, if we are talking about asset management, okay, what are we actually talking about? We are actually talking about the performance risk management. Okay, what is risk? Risk is a possible event that could cause harm or loss or affect the ability to achieve an objective. Okay, so in this case, our objective was to safely, securely, and reliably provide power to our customers, right? So see there, I stated the objective: to safely, securely, and reliably provide power to our customers. Okay, so anything, any action that can hinder this objective is a risk. Okay, any action, and let's see what are those actions, right? So then what we want to do is we want to understand what are those actions, and then we want to see what are the things that we need to do in order to ensure that these actions have the most or have the least impact on the objectives. So, for example, if I take a distribution feeder, okay, the objective of this asset is to safely, securely, and reliably provide power from the substation to the customer. Okay, so that is my objective. Okay, now what are the threats to my objective? Threats to my objective are many. I can have lightning, I can have, you know, trees, trees that can cause faults and basically um, disrupt the power flow. I can have animals that can create faults, right? Now these are things that are not so much in our control, in the sense that they are natural phenomena. There are things you can do, right? But we are talking also about from an assets perspective, right? So any asset here can fail. So for example, the distribution transformer, in the substation can fail. The circuit breaker, the feeder head can fail. The reclosers can fail. The sectionalizers can fail. The towers or the wood poles that you have, those might fail, right? The conductors might break, right? So there are all these different kinds of threats that we need to understand, right? And these are threats that can basically harm or affect the ability to achieve our objectives. So then we need to understand also what are the impacts. So for example, in this case, in this example, if the circuit breaker at the feeder head fails, then we have a big problem, right? That means every customer down that feeder is going to be out of power. So that's a big problem. Okay, so if I understand the failure of the circuit breaker at the substation, the impact is very high. Now, if I take on the other hand the failure of a distribution transformer on a pole top transformer at the end of the feeder, if that fails, what is the impact? The impact is small because maybe there are only 2 or 3 customers connected there, so the impact is small. So you need to understand then in the context of the impacts, what is the impact of the failure associated with each of these assets when these threats happen. Okay, now once you identify the failures or the possible conditions for these failures and you understand the impacts of these failures, the next question you have to ask is, how do you mitigate these identified threats? Okay, so there are 3 obvious ways, right? And this is just from a very generic common sense perspective. In risk management, there are 3 things that you need to know. One is remove the threat. Okay. 2 is strengthen or make the system strong so that even if the threat is there, it doesn't impact the system. Third is, even if the threat happens, make sure that the impact is mitigated. Okay, so let me give you an example here. In the same example, if you're talking about a distribution feeder, right? And let's say we're talking about the failure or the where you have a lot of faults that are caused by trees. In this case, the threat is the tree branch that would come in contact with the live feeder. So if I want to remove that risk, I cut the trees. I basically do tree trimming so that I have enough clearances so that the branches don't touch the electric line. So in that case, I have removed the threat. Okay. So if the threat is gone, then that's good. There is no need to worry about, the risk is gone with it. But that's very difficult to do because I've removed only one threat. There may be other threats, right? In this case, an asset that fails. Why? Because it is very old or it is in very bad condition. So in that case, what can I do? I can inure against the threat. So that means I can say, I know that this circuit breaker at the distribution feeder head is in very bad condition. So let me replace it. Okay, fine. You replace it. So what you've done now is that you have prevented a big failure by making the system strong. In other cases, for example, one of the projects that I did, this was for hurricanes. So as part of the strengthening, we said, let's replace some of the wooden poles with steel structures, because that happened to be the place where there would be a lot of wind, and the poles would break. So in that case, we basically made the system strong against that threat. And the threat in that case was wind that would basically knock these poles down. The third one, mitigate the impact, is basically a situation where, we're saying, even if, we have the line fails, let's say in this case, the poles break. If you want to mitigate the impact, we basically provide, an alternate way to serve the customers. So if there's some local, generation available, right? Then that local generation, for example, diesel sets or whatever that are distributed to these customers, that can help these customers stay, intact. That can help these customers basically have power for the time when the repairs are being effected. So in that case, we have mitigated the impact, right? So these are the three main strategies, and we need to understand this from the perspective of asset performance management. Okay, so now let me do the next thing. I will go into the next slide. Next slide basically talks about what are the use cases from for asset performance management from the perspective of these people who use such a system. Okay, so there are four different types of people who essentially use an APM system, and in particular looking at substation assets. Who are these people? So there is one who is basically the asset engineer. This is the field asset engineer, or the reliability engineer. Then there's basically the manager who is looking at it more also from a financial perspective. Then here is the planner who is looking at things from the perspective of what do I need to do next? How do I plan for things in the future? And then here is the field technician who basically needs to understand, things in the field. So let's look at each one of these people, these persona. Okay. So from a substation engineer's perspective, right, the questions are, what is the condition of my asset? So if I have, a bunch of assets in my substation, we want to understand what is the condition of my asset. At least that is this person's responsibility. He needs to understand what is the condition of my asset. He needs to also ask the question, what is the risk of failure of my asset, right? And as an engineer, you also need to understand why is the asset in the state, right? What is the threat? What is the threat, and how is that threat, affecting the asset and making the asset, in a condition where it is not performing to its optimal level. So then the next question is, how to spot an imminent asset failure, right? How do I know if this thing is going to survive in the, next 24 hours? Is it going to be, available in the next 24 hours? When is it going to fail, right? He's also interested in asking what short-term remedial actions need to be taken. This is mainly from a maintenance perspective, so that once those maintenance actions are taken, then he can tell the field worker, what needs to be done. Okay. Then there are other questions. It's like, what happens if the action is taken? Also, what happens if the action is not taken, right? So if you don't take the action, are you going to have a reliability related problem? So these are some of the use cases. These are some of the questions that the asset engineer is asking. From a financial perspective, in this case, this is going to be the CEO or the manager of the asset strategy group, right? This person essentially is interested in understanding what is the system level risk that we have. What is the fleet-wide risk? So we want to understand exactly how these risks are trending with time. Why is this important? Because this person here, is continuously allocating, resources, allocating money to be spent on improving the electric system. So if you see that these risks are increasing with time, then clearly the work that you're doing is not the correct work. You're spending money where it is not needed, which means what? If you go back to the first thing that we talked about, which was ISO 55000 line of sight principle, right? Line of sight principle basically says spend your money where you can get the most return for your money, right? So in this case, by looking at the risk trend over time, and if you see that that risk trend is actually, instead of decreasing, it is going up, then we have a problem. So that is the question that this person is asking. Then this person is also interested in what is the long-term action that needs to be taken to mitigate this risk. So that means 3 years from now, 5 years from now, I want to make sure this asset is good. What do I need to do? And that is where this person interacts with the planner. And the planner is basically saying, okay, these are the different kinds of things that you can do to ensure that level of performance. Okay? And this person is also asking the question, what is the most return for the money spent? Am I justified in replacing section analyzers? Am I justified in doing more tree trimming? Am I justified in doing more animal prevention, from for example, making sure that animals cannot come in contact with lines? So how do you basically justify these investments? Because that is what this role is responsible for. Now let's talk about this role here. This is basically the field engineer. The field engineer needs to know, and he interacts with this, the asset engineer. The field engineer needs to know where is the bad actor. When I say bad actor, that basically means where is the asset that has a problem? How do I get to that asset, right? So you need to make sure that this person has the right directions, GPS, directions to go there. When the person arrives there, he or she needs to know what is the problem, right? And the engineer here can basically pass on that information to the field engineer here and say, this is the problem, this is the action you need to take. Then the question this person also asks is, okay, I know the problem, I know what to do, but now do I have the right parts? Do I have the right skills, to take this remedial action, right? So this interaction here now is not only with the APM, but is also with respect to the work management system, because this needs to be coordinated from the work management system. And when we talk about parts and labor skills and all that, now we are talking about things that need to be coordinated with the supply chain. So now you see how all the different pieces are coming together, right? So if work needs to be get done in the field, you need to make sure that you have the right person. You need to make sure that you also have the right uh, uh, parts, right? So that the work can be done satisfactorily. Now, last but not the least, let's talk about the role of this person here. This person here is the planner, and this planner is also looking at long-term planning. He's also looking at it from the perspective of how does the load grow. If we are going to build a new mall, if you're going to build a new airport, if you're going to build a new railway station, there is going to be load growth. How do we plan for expanding the system, and how do we plan for capital budgets so that we are able to build the system that is needed. This role is also responsible for investments related to improving or maintaining current asset performance levels, so that they are working to appropriate standards, um, and ensuring that the decisions related to whether you repair or you replace are taken at the right time, when, and how. So meaning, the coordination has to happen between all of these different persona here in order to satisfy the objective. What is the objective? Again, I repeat, it is essentially to get power from the utility side to the customer in a secure, safe, and reliable manner. Okay, so that is the objective to which all of these actors, all of these persona are coordinating their efforts in order to be able to achieve that objective. Okay. Okay, so let me talk about the next step. And this next step is more for the interaction between, in this case, the planner, and also, in this case, this persona here, who's essentially responsible for the money related to asset management. So these two interact with each other, and that interaction essentially is this process called asset investment planning. And the asset investment planning use cases include, trying to find answers to these questions here, right? If I have a given budget, what is the optimal portfolio of projects to execute? Now, I cannot do all of the projects. I cannot take all of the remedial actions because I don't have the money. So for the budget that I have, what can I do? What must I do? And what is the best set of actions for me to do? Then the next question is, for a given level of risk, assuming that I have, an understanding of the level of risk, what is the minimum budget requirement? Okay, and this is important again because from the perspective of, a regulated utility, typically, you have to make the case to the regulator to say, I need so many $1 million for project, A, project B, project C, in order to do all of these activities. But you need to have a good justification for that. And you need to be able to convince the regulator to say, okay, if I do this project, I am mitigating this risk. If I do this project, I'm mitigating this risk. And mitigating all these risks is good from the customer's perspective, right? So that justification needs to be done. Also, we need to understand, the system risk change as a function of time. So that means as time changes, as we go forward, how things change. What is the cost for mitigating a unit of risk, right? And again, line of sight principle applies. You want to spend, money so that you're mitigating risk. You don't want to spend money where no risk is being mitigated. Then that wouldn't be very useful use of your money, right? Then last but not the least, what in-flight adjustments are needed to achieve the desired level of risk mitigation? I put this in quotes because think of it this way, an electric utility is live. At any given point of time, there is at least one asset there that has power, which means what? There is no dead part of your system. It is always live. The idea is, what changes do you need to make? What adjustments do you need to make so that you're able to keep the entire machine, and in this case, I'm talking about the entire power system, live without, sacrificing or without compromising on your objectives of being able to supply, your customers with reliable, secure, and safe power. Okay. Okay. I will get to this one final slide, and we'll take a little small break for some questions because we have covered a lot of things here. Let me just cover this one slide here. So asset management is really the art and the science of decision making. Okay. How do you make decisions? Okay. That is the key question for an asset manager. Now, decisions can be made in many ways. Okay, so if you look at these different principles here, you have decisions that are made by consensus, which means, people sit together in a room, they discuss, they come up with a consensus, they say, okay, we do this. People can vote, you put 10 people in a room, put all the different options out there, 3 people can vote for something, 5 people can vote for something else. Okay. The other is you can get a decision based on a consultative approach, provide all of the pros and cons to all of the different people, and you can consult with them and then walk them through and ultimately come to a decision. Consulting. Command is basically, you say, the chief executive or, the main person in charge basically says, this is my vision, this is what needs to be done. Now notice something here on this risk and time scale here. This takes very less time to do, right? Consensus here takes the most amount of time, but it is the lowest risk. So one thing to understand here is in asset management, if you want to do the right thing, the decisions cannot be just done at the command level. They actually need to have the people actually need to buy into that idea. The people really need to be participants in the decision-making process. Okay. Otherwise, no decisions will get implemented properly. So each person has to have, that ownership in that decision. So here, I've listed some of the steps here. You list all the pros and cons of a particular action. You develop a consistent scoring methodology, right? In this case, we're basically saying, what is the way in which you will look at making the decision. Then you sit down in a group and you basically list the pros and cons of each of these ideas, get a score, and also consider the do nothing option, because sometimes doing nothing may be the best thing to do. Then you compare, contrast all of these actions. Go back and see if you have forgotten something, and then start looking at, next steps, and then you make your decision. Okay. All right. Let me take a small break here. I've been talking for about an hour. I want to make sure that we are all on the same page. We are all understanding, and we are, proceeding in the right direction. Sebastian, any questions? What I will do next is I will go into some more details, more deep dive of actual data analytics as applied to an electric utility system.
Okay, Siri, there is no hands up. ¿Hay alguna pregunta, algo que quieran, una pregunta intermedia? Sí, ya hay una mano alzada. Aprovechemos señor Paneso, por favor, proceda a prender su micrófono y realice la pregunta. Gracias.
Okay, thank you, Sebastian. Thank you, Mr. Varadan. Thank you so much for this presentation. Now, sometimes utilities are ambitious in the achieves that they want to get. Then I want to know when you start a project or a research using data, the question you are trying to answer is given by the client or is a consensus between both parties, taking into account the available data. Thank you.
Okay. I understand your question as how do you basically define the questions related to the objectives? Is that your question?
Yes, sir.
Okay. All right. So let's see. In this case, if we are looking at a an electric utility, right? The objective of the electric utility is clear. The objective is to basically provide electricity to the customer in a safe, secure, and reliable manner, right? So the objective is clear. Now, how this can be achieved can be in many different ways, okay? So let us say in this example, I have one feeder that basically goes from substation that is located in one place. It goes through a mountainous region and it has many customers as you go along this mountainous region, and then it's a feeder about maybe 100, about 25 to 30 kilometers long from the substation. Okay. Now let's say the reliability on this feeder is poor. Okay. Okay. Now how do we know it is poor? Well, we have the data that is telling us that it is poor. We have a lot of customers that are complaining. We have a lot of customers that are telling us that the interruption times are very long, and they're telling us that they have a large number of interruptions. So we have two measures that we are getting from the data that's basically telling us that the performance on this feeder is poor. Okay. So the objective now, we know what the problem is. We've understood that something needs to be done. Okay. Next question then is, what is causing this problem? Okay. So we know that there are a large number of outages. We know that the outage duration is large. Now, what are the causes for this? Okay. So this requires some additional research, right? So where does that data lie? You can now go to your outage management system, or you can go to your SCADA system to basically see what are the interruptions and the times of the interruptions. So let's say we go into the outage management system. In your outage management system, you can look at the average, duration of an outage. You can look at the number of outages that you've had on this feeder. Okay. You can also look at what are the different causes for these outages. You can also look at equipment that have failed, on this feeder. Okay. So now you have further information about, this problem. So now you can look at the next step. Okay. Let's say, this is a mountainous route, right? Because of the feeder being in the mountainous region. So one of the problems that you can also see is that the roads that lead to these different locations is very difficult for a big truck to go. So that you've identified as being an issue. Okay, good. What are the mitigating mechanisms now, right? So mitigating mechanisms now is you can look at can you make the towers stronger? Can you make the lines stronger? Can you make other things, and these are all remedial actions that basically go to improving the reliability, right? So then the question becomes, which one of these actions gives you the most return for your money? When I say return for your money, if I spend $1, am I increasing my reliability by 10%? Am I increasing my reliability by 20%? Am I increasing it by 30%? So I want to make sure that for the dollar I spend, I want the highest return. I want 30% improvement in reliability. That is the sort of decision that needs to be made. Okay, so in this example, what I've walked you through is solving a problem, involves multiple pieces. One is you need to understand why. You need to understand what are the metrics that basically allow you to measure the problem or the impact of the problem. Then you need to understand, not only the engineering aspects, but you also need to understand the physical aspects. It could be that, your, crews cannot get to the right location because they don't have a way to identify where the outage or where the problem is happening, right? So these are all the different things that need to be understood. Then you need to come up with solutions. Then you need to look at all of these solutions and say, okay, this is the best solution to take. Why? Because it is the one that gives you the most return for your efforts. So this is the overall process that goes on in the asset management. Okay. I'm sorry I gave you such a long answer, but you asked a very good question, and it required a long answer. Does that make sense?
It's okay, and thank you, Mr. Varadan.
Okay, sure. Sebastian, shall we proceed?
Yes, there is no more hands up right now.
All right, very good. Okay, let's look at next. Let's do a deep dive into a transformer asset. Okay. So in this case, the deep dive I want to do is I want to understand what is the transformer's risk of failure now and in the future based on different what if conditions, right? Okay. So I need to understand, my objective is clear. My objective is I want to understand what is the a given transformer's risk of failure. I want to come up with some sort of a measure that basically says the probability of failure of a transformer is some number, right? And that number is what needs to be ultimately determined. Okay, so how do I go about doing a problem like this? First, I need to understand, the electrical asset. In this case, I need to understand, what is the transformer voltage. I need to understand what is the rating. I need to understand who is the manufacturer. I need to understand how is the transformer connected in the network. I need to understand, you know, um, the basic information, right, related to the nameplate. Okay. Next, I need to understand for that particular transformer, what are the different failure modes? Okay. So when I say failure modes of a transformer, how does it fail? How does a transformer fail? When it fails, does it fail because of dielectric problem? Does it fail because of a short circuit problem? Does it fail because of accessory problem, right? So let's say the fans failed and so therefore transformer overheated. So we need to understand the different ways in which the asset can fail, okay? Then the other thing we need to understand is for each of these failures, what are the parameters that can define and describe these failures, right? So for example, if I'm talking about the failure of an accessory like the fan in a transformer, the parameter that I will look at is I will look at to see how many times the fan came on and off in a day, right? So that's the parameter that I will monitor. And if I see that the fan is not coming on, and at when it is hot, then I know that there's a failure that's going to happen soon because the transformer is not getting cooled. So the thing is we need to identify all the relevant parameters that are relevant to each failure mode. Okay. Now understand that there is going to be correlations between these parameters that you measure. So for example, a transformer may fail, and one parameter that you look at may be indicative of multiple failure modes. Okay, that's possible. Okay, next question is, do you have access to all of these parameters at the right frequency and the right granularity, right? Example here is, for example, if I'm looking at dielectric failures, then I need to be looking at the oil. I need to be looking at the quality of the oil. I need to be looking at, the moisture content and so on. But the question is, how often do I need it? Do I need it every second? Do I need it every hour? Do I need it once in 6 months? Okay. So these are the next questions that you need to ask, right? What is the frequency you need to get it at? And what is the granularity, in the sense, how accurate does it need to be? Can I say, 10 parts per million, or should I actually go into 10.35 parts per million, right? So what is that level of granularity that is needed in order for this parameter to be interpreted in the right way? Okay. Then the next question also we need to know is, how do we establish the appropriate thresholds for each parameter? So for example, let's say I'm monitoring the voltage for a transformer, and we know that it's a 500 kV transformer, and 500 kV plus or minus 10% is okay, if you're looking at the voltage. Plus or minus 10% is the threshold value. If it goes outside of those threshold values, so if it goes 500 kV plus 10% of that, which is 50 kV on the other side, or 50 kV on this side, then I know we have a problem. Those are the thresholds that we need to understand. Okay. Then the next thing we also need to understand is, how are these different parameters correlated, right? And that is the difficult part, because when we look at data in data analytics, you can correlate, one parameter with another parameter. It's very simple to do. It's just a statistical formulation. But the question there to understand is one causing the other? Is there a causal relationship? Because at the end of the day, two sets of data can be correlated, but they may have, no causation at all. And so it is important to understand the causal relationships of these parameters, right? And then can you look at the next step, which is, can you correlate the physical actions, in this case, anecdotal or manufacturer recommended, to these parameters? So, for example, we know that if transformers are made, at a particular age, of transformers, the paper that is used in there is of a material that, is subject to more failures than, if it is used another material. So do we have that sort of expertise related to, the transformer, and from a design perspective, right? So now the question is, how do you put all of this together? Okay. That is really, in this case, we're looking at one transformer. We're trying to understand that one transformer from the perspective of the data that it creates. Okay? So I have a simple example here that I will talk about it in just a little bit. If we are looking at transformers, the transformer data comes in many forms. So there are, depending upon the sensors that you have, partial discharge sensors, you have dissolved gas analysis, which basically is looking at all of the gas data in the transformer, because at the end of the day, a transformer has chemistry. There's oil inside there, and the chemistry of the oil essentially is something that can tell you something about the transformer. Then there are standard oil tests that basically look at interfacial tension, that look at moisture content, and other things. There's electrical data, which is voltage, current, phasors measurements. There's visual data, which is infrared imaging, robotic and visual inspections. There are maintenance logs. Again, in this case, we are talking about unstructured data, right? There's operational data history, which is essentially, the voltage, current, the information related to frequency changes, and so on. That is all maintained in the operational history. The question is, how do you make sense of it all? I have this example here just to show you that in this case, if I have, a person who's not able to see, um, you know, depending upon, what they feel, depending upon the data that is perceived, right? They will imagine this to be something. For example, here in this case, you know, touching this animal here, this person is thinking it is like a wall. Touching, another part of this animal here, this person is thinking, oh, this is like a spear. Touching another part of this person is thinking, oh, this is like a snake. Touching this part, this person is thinking it is a tree. Touching another part, this person thinking it's a fan. And this person here is thinking, oh, this looks like a rope. But guess what? They are all correct, but they're also all wrong. Why? Because at the end of the day, this is the overall picture that we want. We want to see the elephant. In our case, we want to see the transformer. We don't want to see the individual pieces. The individual pieces provide us information, but the role of data analytics is incomplete without the subject matter expert. The subject matter expert has to put all of this data together and create the big picture. And when we create that big picture, that is essentially like the first dashboard that we saw. We need to tell the story in a complete manner. Okay. And that is the power of data analytics. Not just the numbers, but take the numbers, take the context, look at the expertise, that you have with respect to that particular asset, put it all together, and then create the big picture in terms of solving it. Okay. Keep that in mind as we go into the next picture here. So this can become very complicated. If I'm looking at the transformer model, there are active parts, there are bushings, there's a cooling system, there's a tap changer, of course, not for all transformers. There's the dielectric, related parts. There are oil preservations, main tank. Each one of these has multiple parameters. Okay. So if I'm now looking at it, each one of these parameters now has a stream of data that goes with it, right? And each of these data elements can be at different frequencies and different granularity. The idea is looking at that data and understanding all of the different failure modes. How do you create the picture of the health of the transformer? Okay, that is really the problem that we are trying to solve in this case, right? We are doing this for one transformer, but remember, if you can do it for one transformer, the same logic can be replicated for all the other transformers. So we can do this now for 1,000 transformers. We can do it for 10,000 transformers. As long as you have the data, as long as you have the correct data that is coming in, and as long as you have the algorithm that is essentially ingesting all of this data and making sense of that data. Okay. So now, how do you make sense of all of that data? So we want to create a risk of failure. That risk of failure is defined as probability of failure and the importance. Okay, the importance can be calculated in a different way because that involves financial components. Let's leave that for now. Let's just look at the probability of failure. Now we look at how many ways in which the transformer can fail. There's a short circuit, probability of failure, dielectric, high temperature, accessories, and miscellaneous. How do we know this? We know this based on the history. We know this based on our experience. We know this based on our study of transformers over, many years of, providing services to the electric utilities. Now, in each one of these, we've identified, that these are the different ways in things fail. And these are the different things that need to be measured. So for example, if there's a failure because of thermal degradation, then the parameters that need to be looked at are parameters related to polymerization, right? So this chart is very important to have, because this essentially says, okay, for each of these failures here, we know what parameters to look at. We basically know from industry knowledge and from our own experience what the threshold should be, and we understand the correlation between each of these different pieces of information. Putting it all together ultimately gets you this failure probability and the risk of failure. Yeah. Okay, so next step is, how do we put all of these different pieces together in the in a large asset performance management sort of structure? So if I'm looking at this software here, I'm looking at different assets here, which include transformers, breakers, batteries, motors, turbines. There is data that is being collected in a historian. There is data that is being calculated here from a criticality analysis perspective. There is enterprise data associated for each one of these assets. The idea is we want to ingest all of this data and then basically do this sort of a risk characterization. So we want to say, okay, these transformers are in the red zone, these transformers are in the yellow zone, these transformers in the green zone. Based on this, we want to create maintenance actions, maintenance priority dashboard. Based on this, we want to create replacement actions, replacement priority dashboard. This interacts with the work management system so that we can go and then solve the maintenance related work. This interacts with capital planning so that we can then plan for replacements and so on. Okay, so this is the overall picture that we are looking at in terms of solving the asset performance management. Okay. If I look at some of the state of the art, and this is some of the projects that we have that I have been personally involved in at some of the utilities, we have this sort of a dashboard, where there is a substation summary, based on the different charts that we have. We know what are the different assets. We have number of issues. We can look at these by open issues by substation, and these are issues that have been identified based on running the models. We can look at all of the risks associated with all of the assets. So we have risks that are classified by red, yellow, and green. Red means immediate action needed. Yellow means action needed urgently, but not right now. Green means no action needed. So if you look at something like this, we have essentially addressed all of the questions related to asset management. What are my assets? We are basically saying these are transformers or circuit breakers or whatever. We are saying, where are my assets? We know exactly where the assets are, looking at the map. We know the condition of these assets, and we also have issues that have been identified, and these issues are now issues that need to be taken by to the next step, which is the work that needs to be done. Okay. So this is essentially where utilities currently are going. I have been involved in at least 10, 12 projects doing this kind of work for our customers, and it's been very useful for them, because they are able to understand where to invest their money. They are able to understand how to improve the reliability. They're able to understand how to work more effectively, more efficiently, and they've also learned to understand how to allocate their capital budget more effectively, more optimally. So um, I will again stop a little bit briefly here and see if you have any questions. I have a very small example, and I will walk through it really quick, because I know we have already kind of gone over the 1.5 hour limit for my lecture, so I want to be aware of the time. Sebastian, we're doing okay on time?
Yes, okay, but I don't know if si alguien tiene una pregunta en este momento para Siri o continuamos y ya después al final hacemos las preguntas. I was asking if someone has a question now or we left to the final.
Okay.
No, there is no hands up.
Oh, all right.
Okay.
So now let's look at a practical example. Okay. So on the right hand side, I have a picture. I have a picture of a transformer, and I have these three phases here, and we are looking at infrared transformer here, infrared image, and I noticed that one of these is running hot. It's very hot. These other ones are okay. So the problem, okay, we have overheating in one phase of a transformer is seen in the infrared image. Okay, we see that. I give you further data. For the nameplate, we have the rated current is 1050 amperes. And we have a measurement here of the current, which is 1000 amperes, which is below the rated current. Okay, 1000 is below the rated current here. Why is there overheating? Okay, so I give you a few minutes to just think about
bad connection.
Can you hear me?
Bad connection. But in the hot spot because of the bad connection. Maybe.
Maybe, yes. Very good.
Insulation.
Insulation, yes, very good.
I think that we need more information to be sure that what is the problem.
Okay, all right. So that's the right. All of you are right because you're thinking about what could be wrong, and certainly we need to do more investigation. Okay, so what is the logical approach? You say, okay, you know what? Let me do some measurements. Let me do some additional measurements. I think what I have here is not enough. I know that I have some problem, but it's not enough. I don't know why it is happening. So let's say now I start monitoring and I set up instrumentation to capture the waveform of the current, and the current waveform is shown here. Okay, current in amperes, and this is basically the time, milliseconds. Okay, so if you look at this current here, something tells you something is not right. And if I zoom into this part here, basically you see this current here is doing all kinds of funny things, right? Okay, so that tells you, okay, you know, so now you've got additional information. You're like, the current in this transformer is full of harmonics. So you say, okay, let me now see exactly what are these harmonics doing. So what is the next step you do? You do a Fourier series, right? So you basically break this current into its Fourier components. So I get, in the time domain, this voltage waveform is equal to the voltage waveform at the fundamental frequency, then the third harmonic frequency, fifth harmonic frequency in this case. In the frequency domain, this is the voltage waveform that shows 1000 amps at fundamental, about 450, little more than 400 something amps at the third harmonic and some fifth harmonic. So this is what the Fourier spectrum looks like for this one here, for this one here, and for this one here, right? So you guys are familiar with this, right? And this is an engineering tool that we have. Most electrical engineers and most mathematicians know how to do this. So now the question is, okay, we have current, we know that this current has harmonics. Okay, so let me look at the next step. Let's look at the summary of the Fourier series. And that's basically, this is the summary of the Fourier series. So you have I1 is 1000, I3 is, I1 is the RMS value of the fundamental, I3 is the RMS value of the third harmonic, I5 is the RMS value of the fifth harmonic. If I look at IRMS, this is 1151. Our rated current that came from the nameplate is 1050, right? This is greater than this, so we have overheating. Okay. Now I'm just giving you an example here of how to basically go about a problem, right? Now you all were extremely practical when you said bad connection and when you said insulation problem. Now that is based on your experience, right? That is based on your experience, which means there is anecdotal data. Very good. Many times that is enough to solve the problem. But in some cases you might need to dig a little bit deeper. And what that means is you need to basically get to the next level, which is installing some additional sensors. In this case, it happens to be harmonics. It could be something else. Maybe there's some other thing going on. A simple example here was, we did some more measurements, and then we used data analytics tools. Fourier series is basically a data analytics tool. And then we basically reconstructed the problem. And we see in this case that, okay, we know that the RMS current of the overall current is higher. What we measured earlier was just the fundamental component. So this is the sort of logical thinking, that one would need in order to be able to solve problems, right? So the example here should tell you some things. One is you should know the subject matter, which means I cannot take somebody who's a pure mathematician and give him this problem and say, solve this. You're not going to get anything because that person is not going to know what to do, right? So you need subject matter expertise. You need somebody who knows, okay, here is a transformer, there's a current that flows in the phase, and that current increase, the load is actually causing some problems. So you need that information, you need that knowledge. So that is what we are calling subject matter expertise. Once you know that, then you need to understand the data analytics tools that are out there. You need to understand, the sensors that you might install, right? So in the case of a transformer, you can install DGA sensors. You can install, they call them different vendors have different sensors, hydrants. There's this to measure DGA. There are partial discharge sensors. There are so many different sensors that you can install for a transformer. Then the question is, how do you take all of this to make sense, right? Now, those are the practical problems associated with, doing something like this. Okay, so I want to present the overall picture so that you get an idea of how we solve issues, how we use the principles of data analytics, and how we put all of the different pieces together. Okay, so let me just jump to the summary here. In summary, what I'd like to say is, look, numbers are there everywhere, okay? But numbers don't tell the whole story. You have to ask the right questions, okay? And you have to understand the context. So for example, if we looked at the numbers earlier, we understood that the numbers were in the context of a transformer. We understood that the numbers were in the context of assessing the risk of failure of a transformer. Then now we can build up the story, supported by numbers. Very good. Remember also, when you look at a problem, you try to look at all of the facts. And that's why, asset management is something that we always say is a holistic. We need to look at everything before we jump to a conclusion. If you cherry pick, okay, and cherry pick means you only look at certain numbers. That is not a good way to go, because you can make a good conclusion look bad and you can make a bad conclusion look good. So the details matter. The truth, lies in the details. You have to get into the details, and the details in the right context. Okay. Asset management is very holistic. You need to look at multiple factors. It is the ultimate exercise in financial engineering, dealing with all aspects of the life cycle of an asset. Okay, so if you are to look at asset management as a whole, you need to understand how all the different pieces fit together. Okay, data is the most important asset when we talk about asset management today. Because if you have the data, then you can convert that data into information, and you can convert that information into actions, and then decide what actions you need to take. Again, you need to have your objectives set first. Okay. If you're an electric utility, your objective is very clear: provide power in a safe, secure, reliable manner. If you are doing another sort of business, then you have specific objectives, you have specific assets that help you achieve those objectives, and then you go apply the same principles that we've gone through here. Okay. To me, having been in this as an electrical engineer for now close to 31 years, what I see is that the asset management solves a lot of real life problems. You need to understand not just engineering, not just mathematics, not just statistics, not just the physics of how assets work, but you have to recognize how to put it all together. And I think that synergy of all of that is essentially what helps you be a good asset manager. How to to understand asset management. Because at the end of the day, you need to make sure that the financial aspects are satisfied. You need to make sure the engineering aspects are satisfied. You need to make sure that the customer aspects are satisfied, right? So putting it all together is the fun and the beauty of asset management. Okay? So I'm very fortunate to be working in this field, and hoping that you are inspired by this talk, and you will look at similarly putting things that you have learned from different components, different parts of your engineering careers, to solve something that is a bigger problem than any one particular piece. Okay. Okay, I will stop at this point. I think we have exceeded our time. So Sebastian, thank you very much. I will turn the floor back to you and open the floor for any questions.
Okay, thank you so much, Siri. Let's see if anyone different than me, because I have 4 of them, just myself, but a small question, no large. Okay, Franklin Kilamba, start the question, please.
Hello, Siri. Thanks for the presentation. It was all very clear. I have a question regarding your last example. Let's say you mentioned that is a real problem, right? And how do you go about to find the answer to the harmonics? Because like the experience will dictate that you will think vibration or something is not well fastened, the terminal there in the transformer, and then you go by eliminating things, and finally you can get the answer of the harmonics. Because I don't think if just the subject matter expert will go directly and say, oh, this is a harmonics problem.
You're absolutely right. This was an example. It's not a real example. It's an example that I made up. Okay, I made this example to show you that there are different things that you need to think about in solving the problem. Right. My point there was to show you that there are, depending upon what you suspect, And depending upon what the data tells you, you can go into different conclusions, right? So the idea here was to basically show you how you can use data, install the sensors, get the data, do something with that data, and then make some conclusions. Okay, this was by no means something that you should take as a real example. It was I just wanted to show you an example of how you could use data analytics.
Great. Thank you so much.
Sure. Any other questions? I will add again, to the problem that we saw there. Again, perhaps 6 out of 10 times, it's probably a bad connection or loose connection. Now, how do you know that? Again, you know that because of your experience, right? Very good. But what if it is not a loose connection? Then what happens? How do you find the next problem, right? Again, for that, you need to dig a little further. So the idea is knowing something versus knowing that it is not something that you know. How do you get into the next sort of assessments? And what should you do? That was really the idea of that example.
Okay. Siri, I will continue with my questions, okay?
Please do.
Okay. Okay. It started like a proper experience. I was thinking studying reliability theory in order to think about um, optimized designs in electrical systems.
Mm-hmm.
But with your presentation, I feel like my eyes were open because I think this kind of designs for optimizing have been like assets, uh, taking into account planning, financial things, and operation. For the reason, I want to ask you if you recommend a specific or book or source of asset management in electrical systems.
Yes, in fact, there are quite a few books. I very recently read something. Let me show you. Uh, this is something that I recently bought this book.
But
Can you see? Can you see the book?
no, the screen, but mm-mm.
No. Okay. It's called Infrastructure Management, Infrastructure Asset Management with Power System Applications. It's written by Lena Bertling. We have worked together in the past, a part of IEEE. She just wrote this book. It's less than a year old. This is one book. There is a tutorial that the IEEE did a while back that covers the areas of reliability, maintenance, um, and other topics related to electric assets. And so they basically look at transmission assets and distribution assets
Okay.
from a maintenance perspective. So I can send you some of those references if you.
Okay.
Yeah.
Thank you so much.
So let me write that down. Hold on, otherwise I'll
Oh
forget.
no, but I write a mail for you for this
Okay.
thing. Okay, no, for not for no problem. Uh, Another question. There is a business for consultancy in this kind of. I understand that it's natural for enterprises like ABB Hitachi to bring this service, the studies and the service, because you got the technology and the equipment to do it. But I'm asking you, for example, companies like Burns. Quanta that plan this kind of strategy for a specific utility, and then go out for a enterprise like ABB Hitachi for RD solution. Do you understand my idea? I think this is quite of blurry, my question, but is there is a company consulting company that specifies or analyze the problem, then go for an enterprise like yours.
Mm-hmm. Yeah, there are many companies that consulting companies that do this work. There's a company called DNV, which used to be KEMA before. Black and Veatch does this. Accenture does this. So there are a lot of companies that basically do. Quanta is another great example. They specialize in the concepts that I presented here, in terms of how to look at different data sources, how can you develop the asset strategy at the enterprise level, and they can also help utilities write down the specifications for a software solution that will address all of these issues, right? And the software specifications that are written are then published, and though that's a RFP, open bid, and a company like mine, Hitachi ABB or any other company, might then see that and then say, okay, we have a product that satisfies these requirements, let's bid for this job. And then there's a competitive process by which the right vendor is selected. Okay, so yes, there are companies that do this work, and I mentioned some of these already. Quanta, Black and Veatch, DNV, these are consulting companies that help utilities come up with the specifications for these things. I work mainly on the vendor side, so which means we build solutions, we expect or we anticipate these needs. We build solutions based on the anticipated needs, and try to solve these problems ahead of time. So a lot of times what happens is these consultants will create specifications. In many cases, the products that are created satisfy 100% of the requirements. In many cases, the consultants will have more requirements than what the product specifies, in which case there is a partial compliance, and then the understanding is that the product needs to be complemented with all of the extra functionality as part of the implementation process. So that's typically how we are able to satisfy our customers' needs, right? But at the end of the day, we are learning from each other. So the utility is learning about what needs to happen. They're working with consultants who are telling them, okay, these are all the things that are available, so you need to ask for these things. And then vendors are also talking to these consultants to know what customers are asking for. And we're building products on our side, so it's an ecosystem in which everybody is learning from each other.
Okay, thank you so much. That are all my questions. I don't see any other hand up. I think that is all for today. Thank you so much, Siri, and really nice presentation. I like so much. I think that the people that is here think the same. I think that is not so much people because of the language. Also, the people now he's thinking about the language as a whole, and think
Yes.
the but if we don't try to understand, it can be hard to
Right.
cross this wall.
Yeah, so one thing that we do is we do recognize that from the perspective of the user, the business need is the same, right? You're an electric utility, you need to satisfy certain problems. from the perspective of making sure that the regional differences are accounted for, we do provide situations where language is not an issue, meaning that the software solutions could be in multiple languages. And then on the back end, we ensure that formats, for example, using the right local currency, using the right dot versus comma, these sorts of things are accounted for in making those regional sorts of customizations, right? So these are all things that most of the vendors will do. At the end of the day, what you need to look for is the business requirement met with these solutions. And if that's the case, then you have a good vendor who can provide you a good solution. So.
Okay, there is a comment from, I will check the chat. I don't know if you are reading it. There is a Habit Iqbal. Thanks, Siri, for your comprehensive and enlightening presentation. It's really useful. He's told him.
Oh, thank you. Thank you, Javed.
Okay, and I think that's all. Thank you so much again. It's a really good presentation. Okay, goodbye.
Yeah, thank you again. Thank you all very much. I appreciate it. I wish we could have done this in person. I would have loved to be there in Colombia and definitely enjoy, the travel. I enjoy travel, but hopefully in the next, few months or so, the COVID problems are behind us, and we'll be able to do more traveling and make this a more interactive session in person.
Okay, right, thank you so much. Bye.
Thank you very much. Take care. Good night.
Good night.
Bye-bye.
Thanks, Siri. Goodbye.
Thank you. Bye-bye. Thank you.